In this video, I will show you how to find the resultant vector when two or more vectors are acting together, even when the directions are not simple directions like north, south, east, or west. I will be using this four-step method that works every time, and I will be using this clever graphic organizer to keep my work organized. I recommend that you do the same. A ship sails 50 miles west 20 degrees north and then turns to sail 30 miles west 85 degrees north. Find the distance and the direction of the ship from the original starting point. So we can think of this trip as being divided up into two smaller trips, and each of these smaller trips is a vector because it has a magnitude and a direction. Record your work in a chart like this. We'll have a column for trip 1, a column for trip 2, and a column for the resultant vector. First, we will find the magnitude and direction of each vector. So a ship sails 50 miles, that's the magnitude right there, 50 miles. And the direction is west 20 degrees north. That's going to take a little more thought. West 20 degrees north means start at west and then move 20 degrees towards the north. So I'm going to start at west and then I'm going to turn 20 degrees towards the north, and that is where the vector is. So that means that this angle right here is 20 degrees. Now, for the purposes of this chart, we need the angle that is measured from the positive x-axis counterclockwise. So we need this angle right here instead. Alright, and we call it angle theta. This angle should be 180 degrees minus 20, so this angle should be 160 degrees. So that's the angle that goes on the chart. Okay, so make sure when you're doing the magnitude and direction on this chart, always use the direction measured from the positive x-axis counterclockwise. Alright, let's move on to trip 2. See what was going on. Then turns to sail 30 miles west 85 degrees north. So the 30 miles is the magnitude, so 30 miles. Now that direction, west 85 degrees north. Okay, so west, what was it, 85 degrees. This means start at west and then turn 85 degrees towards north, like this. So the vector should be about here. Where this is 85 degrees. Okay, so again, the angle that we need for the chart is the angle measured from the positive x-axis like this. We call it theta, and this angle should be 180 degrees minus 85, so this should be 95 degrees. So that's the angle that goes on the chart for trip 2. Okay, now look, what I'm really doing is I'm doing this four-step process. Step 1 was to determine the magnitude and direction for each vector. That's what we just did. Now step 2 is to convert the magnitude and direction to component form using this little formula r cosine theta comma r sine theta. Okay, so for trip 1, if I want to convert this to component form, r cosine theta will be 50 cosine 160. And r sine theta will be 50 sine 160. So let's put this in a calculator. So this is what we get. So negative 46.98 and 17.10. So that's the component form for the first vector. Now let's do trip 2. Again, we can find component form by doing r cosine theta. So that will be 30 cosine 95. And now we do r sine theta. So that will be 30 sine 95. Back to the calculator. Check it out. So we get negative 2.61 and 29.89. Alright, that's it for step 2. We converted the magnitude and direction to component form. Step 3, add the vectors to find the resultant vector in component form. So we just need to add these. So I'm just going to add these corresponding components, and I will record them here for the resultant vector. I'm getting negative 49.59 comma 46.99 for my resultant vector. So that's it for step 3. That just leaves step 4. Determine the magnitude and direction of the resultant vector. So I need to take this component form and turn it into magnitude and direction. Let's start with magnitude. For the magnitude, I will just use the magnitude formula. So negative 49.59 squared plus 46.99 squared, square root of all that. I'm getting 68.32. So that's the magnitude of my resultant vector, 68.32, and this is miles. So now we need the direction. Okay, let's see. Negative 49.59 and positive 46.99. That means left and up, or you could think of it as west and north. Either way, we are talking about the second quadrant. So let's draw ourselves a vector in the second quadrant. And let's go ahead and make a little triangle out of it and label the reference angle that we are about to find. Because this first number represents the horizontal component, I'm going to put the negative 49.59 here. This is the vertical component, so 46.99 goes here. We can find the reference angle using tangent. Tangent of r will equal 46.99 over negative 49.59. I am going to ignore the negative sign though, because all I really care about is the positive size of this reference angle. So now I can find the reference angle by doing the inverse tangent of 46.99 over 49.59. So let's just put that in the old calculator. Okay, I'm getting 43.46 degrees for the reference angle. Now, when we record directions on this chart, we always speak about angles that are measured counterclockwise from the positive x-axis. So the angle that we need for the chart is the one that goes like this. All right, this is theta. And theta should be 180 degrees minus this reference angle, so minus 43.46. So that's 136.54 degrees. That is the direction of the resultant vector. So I record it on the chart, 136.54 degrees. Now this is basically the final answer, but this is not the final answer. The reason why is just the way that they gave us the direction in the original problem. There are many ways to give direction. Now on the chart here we converted over to an angle measured from the positive x-axis. But that's not how they gave us the directions in the original problem. They gave us things like west 85 degrees north. So we need to convert this back into the same type of direction that they used in the original problem. So that's not going to change the magnitude, obviously, so I'm just going to recopy the magnitude. So I've got 68.32 miles. But now I'm going to pair that with a new version of the direction. So let's look back at that direction diagram again. Okay, so we want a direction that's in terms of, that's something like west and then some kind of degrees and then north, something like that. So if we start off looking at west, we could get to the resultant vector by turning this many degrees north. So we could think of this this angle, this position, as being west, and then turn 43.46 degrees towards the north. Okay, so this is how we would write that same direction, but using the method that they used in the original problem, which is important. So I'm just going to record that and put a box around it, and then we'll be done. So this is west 43.46 degrees north. Put a box around it. And there you go. Let us do one more problem. A plane is flying 200 miles per hour at a bearing of 320 degrees. It encounters a wind speed of 60 miles per hour, blowing at bearing of 190 degrees. Find the actual bearing and ground speed of the plane. Let us use this graphic organizer to keep our work straight. And we'll set it up like this. We have these two vectors. We have the plane velocity, but I'm just going to put plane. And we have the wind velocity. And in this column, we will record the resultant. All right, that will be the actual bearing and ground speed of the plane. In the first row, we will record the magnitude and direction for both vectors. And in the second row, we will convert to component form x comma y. So in other words, we will follow these 4 steps. Step 1, determine the magnitude and direction for each vector. So, a plane is flying at 200 miles per hour. That's the magnitude, 200 miles per hour. Alright, I'll come back to the direction in a moment. It encounters a wind speed of 60 miles per hour. So that's the magnitude of the wind velocity, 60 miles per hour. So that's the magnitude. Now we need the direction. So the plane is flying at a bearing of 320 degrees. So let's analyze that. A bearing of 320 degrees. Bearing is measured starting from north, and you measure it clockwise as you go around the compass. So let's go 320 degrees clockwise starting at north. So far that's 90 degrees, 180 degrees, 270 degrees. So 320 degrees is definitely going to be here in the second quadrant. So let's draw a vector here in the second quadrant. Okay, so that is our bearing of 320 degrees. Now, for the purposes of this chart, when we talk about magnitude and direction, this direction needs to be measured from the positive x-axis. So we need to really redo this. So we are going to ultimately need this angle, which we call theta. And to figure out what that angle is, we need to start by knowing the reference angle. So we can quickly figure out what this reference angle is. We're going to need that because of the 320. 270 is right here. Now we're talking about bearing. So as we went clockwise from north, it was 90, 180, 270 is here. By the time we got to the actual vector, we were at 320 degrees bearing. So the reference angle is the difference between these two, 320 minus 270. So the reference angle is 50 degrees. Now we can figure out what the direction is as measured from the positive x-axis. This angle should be 180 degrees minus the 50. So that's going to be 130 degrees, which is the angle that we will record on the chart. So we have 130 degrees. Now let's move on to the wind velocity. What did they say about the direction of the wind? The wind is blowing at a bearing of 190 degrees. Okay, let's take a closer look. So we're talking about a bearing of 190 degrees. Again, bearing is measured starting at north and moving clockwise. So if we go 190 degrees, that's going to look like this. 90, 180. So 190 degrees is just going to be a little bit past 180. Alright, so we are definitely talking about a vector in the third quadrant. Now, ultimately, we will need the reference angle, so we might as well find it right now. So let's figure out what this reference angle is. Well, this is 180 degrees so far. If we had gone all the way to west, we would have arrived at 270 degrees bearing. Okay, so because this is 90 going clockwise from north, 90, 180, 270. The vector itself was at 190. So the reference angle is the difference between these two. So 270 minus 190, that's the reference angle. So again, the angle we need for the chart will be measured from the positive x-axis. So we need the angle that's measured this way. And we can use the reference angle to figure out what this is. what this is. We will call this angle theta. At west, we were at 180 degrees. So we went a little bit further. We went 80 degrees further. Look at the reference angle. So that's 180 plus 80. So that's 260 degrees, and that's the angle that we need for the chart. 260 degrees. With that, we have completed the first step. We have determined the magnitude and direction for each vector. Step 2, convert the magnitude and direction to component form using the little formula r cosine theta, comma r sine theta. For the plane, r cosine theta is going to be 200 cosine 130. And r sine theta will be 200 sine 130. Calculator. So these are the values that we're going to get, negative 128.56 and 153.21. So there's your component form for the plane velocity. Let's do the same thing for the wind. Again, r cosine theta for the wind is going to be 60 cosine 260. R sine theta is going to be 60 sine 260. Calculator. So we get negative 10.42 and negative 59.09. So there's the component form for the wind velocity. So that is it for step 2. Now, step 3, we need to add the vectors to find the resultant vector in component form. So I'm just going to add the plane velocity vector and the wind velocity vector. And I'll do that by simply adding the corresponding components. And I will record that here. I'm getting a resultant vector of negative 138.98, comma 94.12. So that's it for step 3. Now it's time for the fourth and final step. Determine the magnitude and direction of the resultant. So I'm going to take this resultant vector that we just found in component form, and I'm going to find the magnitude and direction. Magnitude. I can find the magnitude by doing the magnitude formula. That's going to look like this. Negative 138.98 squared plus 94.12 squared. Calculator. I got 167.85. That is the magnitude of the resultant. I will record it here. That's 167.85 miles per hour. Okay, that's how fast the plane will really be going once you take into account the effect of the wind. Now, how about the direction? Well, considering the horizontal component is negative 1.38, negative 138.98, and positive 94.12. That is left and up, or west and north. So that puts us in the second quadrant. So let's go ahead and draw ourselves a vector into the second quadrant. Now let's make a little triangle out of it around the reference angle, which we can call R. Because this is the horizontal component, the negative 138.98 will go here. And this is the vertical component, so the 94.12 goes here. Now we can find the direction starting with the reference angle using tangent. We know that the tangent of R will equal 94.12 over negative 138.98. Now I am going to erase the negative sign because all I care about is the positive value of R. So the measure of angle R will equal the inverse tangent of 94.12 over 138.98. This looks like a job for the calculator. So I am getting 34.11 degrees. Now, what I need is the angle measured from the positive x-axis, though, because those are the types of angles that we record on the chart. So we need angle theta that goes like this. That's theta. And theta should equal 180 minus R. So 180 minus 34.11. So that's 145.89 degrees, and that goes on the chart. Okay, now this is basically the final answer. Let's check and see if this is the final answer. No, this cannot be the final answer because the way that we write the direction has to match the way that we were given direction in the original problem. And we were given the original direction as a bearing. And in fact, they're specifically asking us what's the actual bearing and ground speed of the plane. So we need to convert this to a bearing. So this is not going to affect the magnitude, so I might as well go ahead and copy the magnitude again for this second version of the magnitude direction. So I'm going to copy down my 167.85 miles per hour. But now I need to pair that with a bearing version of direction. So remember how bearing works, wonderful people. Bearing has to be measured from north. I think I'll use green for this. Bearing has to be measured starting at north and moving clockwise. So this is what the bearing angle looks like. It goes all the way around from north, and it comes all the way back around like this. That's bearing. Okay, so bearing should be, let's be very careful. Starting from north, when I got to east, that was 90 degrees bearing. Okay, maybe I'll put a little 90 over here. When I got to south, that was 180 degree bearing. When I got to west, that was a 270 degree bearing. And then I went a little bit further because of the reference angle. So the last checkpoint I had here was 270. I passed 270. And then I went an additional angle R, which was 34.11 degrees. So this is how we will get the bearing. I'm getting 304.11 degrees. So that is what we will use for the final answer. We will say bearing 304.11 degrees. Put a box around it. So there is the final answer. Hey guys, that's going to do it for this video. Go ahead and click over here to watch the next video, and click over here to subscribe. That way you'll get every new video delivered right to your home screen.